Hello, chemistry students. Today we are going to learn about mole ratios, which will allow us to perform all kinds of chemistry calculations. We'll also introduce stoichiometry, the math of chemistry. And to introduce these concepts, I have here a recipe for making cookies. This requires 2 cups of flour, 1 cup of sugar, 2 eggs, 8 tablespoons of butter, and a ½ cup of chocolate chips. This will make 24 cookies. But what if I wanted to make 36 cookies? How would I modify this recipe? Well, this lesson is all about ratios. And you may have noticed 36 is 1.5 times as many cookies as 24. So I will need 1.5 times all these ingredients. Instead of using 2 cups of flour, I would use 3 cups of flour. Instead of a cup of sugar, I'd use a cup and a half. I'll need 3 eggs, and I'll need 12 tablespoons of butter. And how about the chocolate chips? Well, I just throw in a whole bunch of those. Mole ratios is going to open up a whole new area of chemistry called stoichiometry. This word sounds pretty scary, but looking at the word's roots, we see that stoichion simply means element, while metry means measurement. So we are doing element measurement. Stoichiometry works because of the law of conservation of mass, which was demonstrated by Lavoisier. Stoichiometry will use balanced equations. The coefficients in the equation tell us the ratio of reactants and products. Stoichiometry will also require us to convert a variety of other units into moles. We might convert mass into moles using molar masses we get from the periodic table. We also see that we can convert liters of a gas into moles using the ratio 22.4 liters equals 1 mole at STP. And finally, we see that we can convert particles such as atoms, molecules, and formula units into moles using Avogadro's number. Now we'll look more at this mole ratio. Whenever we begin these problems, we'll want to have a balanced equation. Let's review that process with this equation. In this equation, there are 2 bromine atoms on the left, while there's only 1 on the right. So I double the amount of bromine by adding a 2 in front of sodium bromide to balance the bromines. This will also give me 2 sodiums on the right. So we balance those atoms by writing a 2 in front of sodium. And this balances the equation. If you'd like to add a 1 in front of the bromine, you can, but it's not necessary. These coefficients tell us something important about this equation. They tell the ratio of reactants used and products produced. For example, 2 sodium atoms will require 1 bromine molecule. This will form 2 formula units of sodium bromide. Notice that I use the terms atoms to describe sodium, since it is a single unbonded element. When I describe the bromine, however, I use the term molecule, because it is 2 atoms bonded together with a covalent bond. Finally, when describing sodium bromide, I use the term formula unit, since this is an ionic compound. Let's look at another ratio. What if I had 12 bromine molecules? If there are a dozen bromine molecules, I'll need exactly twice as many sodium atoms, or 2 dozen sodiums. And these amounts will generate 2 dozen sodium bromides. Notice that the ratio here comes from the coefficients of the equation. In another example, we'll consider the mole, a very useful unit in chemistry that allows for a variety of conversions. Suppose that I had 2 moles of sodium atoms. How much bromine would be required to react with 2 moles of sodium? Right, the amount of bromine would be half as much, or 1 mole. And how much product would this form? Yep, 2 moles of sodium bromides. Before we go on, I want to point out something that can trip up new chemistry students. You may have noticed that the total amount of reactants on the left side of the arrow won't equal the total amount of products on the right side. There are 3 moles on the left, but only 2 moles on the right. And you might be thinking, what about Lavoisier's law of conservation of mass? I thought this was always true. And it is, but it only applies to mass. The masses, or grams of reactants, must always equal the masses of products, but not the moles. This has to do with the way products rearrange themselves during the reaction. Well, let's look at a few mole calculations. How many moles of oxygen are required to react with 4.2 moles of carbon? So there are 4.2 moles of carbon, and I'm trying to find out how many moles of oxygen are required. The way to approach this problem is to write down the units we're looking for on the right side of the equal sign. Next, we write down the given over 1 on the left side. The next thing I do is I write in a conversion factor, a number known as the mole-mole ratio. I write moles of carbon on the bottom so that I can cancel this term. On the top, I write moles of oxygen, and I fill in this ratio. I see that there are 2 moles of carbon for every 1 mole of oxygen. 2 moles of carbon, 1 mole of oxygen. I calculate 4.2 divided by 2, and I get 2.1 moles of oxygen. So 2.1 moles of oxygen are required. Let's try another mole ratio problem. How many moles of carbon monoxide can be formed when 3.1 moles of oxygen react? I'm given 3.1 moles of oxygen and must calculate how many moles of carbon monoxide will form. So I write the unknown units after the equal sign and the given over 1 on the left side. Now I fill in the mole ratio in a way that causes the moles oxygen to cancel and gives us moles of carbon monoxide. I'll fill in the mole ratio from the balanced equation with 2 moles of CO for every 1 mole of O2. In this calculation, I will multiply the numbers, since they're both on the top, and get 6.2 moles of carbon monoxide for my answer. And so using mole ratios in chemistry does so much more than simply helping figure out a recipe for making cookies. Now, with the tools we have, we can consider how much hydrochloric acid reacts with calcium carbonate and determine the amount of hydrogen gas that comes from this reaction. And not only can we calculate the number of moles, but with a few conversions we can find liters, grams, and even particles. Isn't this exciting? And you're probably thinking, I want a cookie. Yum.